Hi, this is Shrija Koncharla from EC department. This video is about multiplication of signals which comes under properties of discrete Fourier transform. The agenda of this video comprises of 6 vital points. Let's start a video by throwing some light upon what exactly DFT is and how it is different from CTFT and DTFT. Thereafter, let's continue our discussion by knowing what is meant by multiplication of signals in DFT. Further, let's see what is circular convolution, followed by what's the importance of zero padding in multiplication of signals. Subsequently, by the understanding of circular convolution and zero padding, let's dive into the proof of multiplication of signals. And eventually, let's sum up with an example implemented in MATLAB. So, let's begin with a common question, which is, why yet another transform? After all, we now have Fourier transform for periodic and aperiodic signals in both continuous time and discrete time. Why do we need DFT when we have DTFT and CTFT? So the answer is quite simple. Any signal which is to be stored in computer should be finite. That is, it should have finite number of samples. But in DTFT, we have infinite number of basis functions, which makes it hard for computation. Hence, we go for another transform which is called as DFT, which has finite number of samples or basis functions. Now, as you guys pretty much understood why we need DFT, let us see what exactly DFT is. So DFT is a tool to transform band-limited time domain signal to frequency domain. DFT can be used for both periodic and aperiodic signals. The best part of DFT is that it never cares about signal's periodicity. Now, let us see how we can obtain DFT of a signal x of n. Let x of n be a time-limited signal, that is, it is non-zero for only n values between 0 to l-1. Then, sampling the DTFT of x of n for any samples n greater than l gives DFT of x of n. So as you guys can see, this is the formula for DFT of x of n. Further ahead, let us see what exactly multiplication of two signals in DFT means. Suppose we have two signals x and h. Now multiplying them in the frequency domain is equivalent to the circular convolution of them in the time domain. Now the convolution between x and h is not an ordinary convolution, but rather it is n-point circular convolution. Now you guys might be wondering what this n-point circular convolution is. So let's quickly look through it. So now let's see what is circular convolution. Circular convolution is a special case of periodic convolution, which is the convolution of two periodic functions that have same period. So in particular, the DFT of the product of two discrete sequences, that is x and y, is the periodic convolution of DTFTs of those individual sequences. Now let us see what's the difference between normal or the linear convolution and the circular convolution. In linear convolution, the signal is linear time variant, whereas in circular convolution, it is a periodic signal. Here, you can see the formula for n-point circular convolution. Now, as we roughly understood what circular convolution is, let us see what issues can rise while multiplying two signals and know how can we rectify it. Let us suppose there are two signals x and y with n, l samples respectively. Now if n and l are unequal, then we cannot multiply them. So here comes the concept of zero padding. Zero padding is a method of extending signals by adding zeros, also called as paddings. For circular convolution of x and y to be equivalent, we must pad the vectors with zeros of length at least n plus l minus 1. So this is the concept of zero padding. Now, while we are aware of what zero padding and circular convolution is, let's quickly buckle down onto the proof of multiplication property. Accordingly, as you guys can see, this is the proof for multiplication of two signals. I'd suggest you to pause the video and look through it. Now, let me give a brief overview on this. Now we have two discrete signals x and y. Let z of n be the multiplication of them. So let's see what DFT of z of n is. That is z of k using the synthesis and analysis formulas of DFT. As you can see, by solving, we'll end up with an equation which states that multiplication of two sequences x and y in time domain is equivalent to their circular convolution in frequency domain. Let's now quickly understand how this multiplication of two signals varies in DFT and CTFT. In DFT, the multiplication of two sequences in time domain is equivalent to their circular convolution in frequency domain, whereas in CTFT, multiplication of two sequences in time domain is equivalent to their linear convolution in frequency domain. Eventually, let us look into an example to sum up all the concepts we have looked through so far. Here, we have taken two signals x and y. Now let's see how the graph of circular convolution of them is similar to the multiplication graph in frequency domain. Here's the code of the example. The code will be provided in the comment section, so do explore it. Here, as x and y has unequal number of samples, we have introduced zero padding to x and y and named them as xpad and ypad respectively. Furthermore, we have also found out the multiplication of xpad and ypad in frequency domain and plotted two graphs of them. So let's analyze this graph for any certain value. For instance, let's see how the above and below graph varies for the value of 3. Here, we can observe that both of them bear a same value, which is 10. That is, LHS and RHS in the multiplication formula discussed previously holds valid. Therefore, we can conclude saying that circular convolution of any two discrete sequences in time domain is equivalent to the multiplication of them in frequency domain, or the vice versa. Thank you.